You've probably seen these viral math videos where you're given a figure and you're asked how many triangles you see, with the obvious catch being you probably forget to count maybe the biggest triangle or some of the smallest ones. That is not what this video is about, so I'll just put this guy over here in the corner. But if you get bored with the aim of this video and you feel like counting, I believe there's 18 different triangles in this figure. This video, instead, is about how many triangles are possible given some bit of information. As an example, if I tell you the three sides of a triangle, you're probably going to say that that's going to lead to exactly one triangle possible. Because you'll recall that side, side, side was a method that we could use back in geometry to prove congruence. So if you knew three sides in one triangle were congruent to three sides in another triangle, you'd say that the triangles were congruent and therefore exactly the same, that they were one. However, it's not always the case that three sides, given any three numbers for sides, that you would form one triangle. In fact, it's possible you could not form a triangle at all. As an example, if I were to give you three sides in a triangle and say, hey, they're 5 and 6, and then the other side, that one's going to be a 20. You'd say, no, this doesn't form one triangle. This setup right here is an impossibility. You cannot have any triangles with sides 5, 6, and 20 because this violates the so-called triangle inequality. The triangle inequality specifies that the sum of any two sides of a triangle, let's just call them x and y, they must be greater than the third side. So for any two sides that I pick, if I add them together, I must get a number greater than the third side. And that works all well and good for 6 and 20. If I add 6 and 20, that's certainly greater than 5. And it also works nicely for 5 and 20. If I add those two together, that's certainly greater than 6. However, we do have a big problem here with 5 and 6. It is not true that 5 plus 6 is greater than 20. 5 plus 6 is not greater than 20. And therefore, this problem violates the triangle inequality, and there are no triangles possible. So this makes me wonder, what other situations can arise where you wouldn't have any triangles possible? Or you couldn't have exactly one triangle possible, which is what you might expect. And this is what ties into what we're currently learning with the law of sines and the law of cosines. As another example, suppose I told you that a triangle had angle A equal to, let's say 100 degrees, and it had a side, let's call it B, equal to 5 centimeters, and then it had side A equal to 4 centimeters. We'll talk about, is this a possible triangle or not? When I try to draw this, just like I did with the 5, 6, and the 20, I notice a different problem. In drawing angle A, you notice it is an obtuse triangle. An obtuse triangle is automatically the largest, an obtuse angle is automatically the largest angle in a triangle because the triangle couldn't have two obtuse angles. So this is angle A here, crudely drawn angle A. And then I notice that side A here, that, well, it has to be across from angle A because that's the convention. So side A would go, I guess in yellow, over here. Side A is going to be 4. And that's where we automatically now have a bit of a problem. And that's that the largest angle in the triangle is not across from the largest side in the triangle. So this given information that we had here would form no triangles. Again, no triangles would be possible. because it violates our rule that the largest angle must be across from the largest side. So what we've seen so far, there are some situations in which our common sense is going to lead us to see that, this is maybe a trick question. There are actually no triangles possible given the information that we were handed. As maybe one more example, let's say given a situation where a triangle has a side A of 7, a side B of 8, and maybe an angle C of, let's just say 38 degrees. If I am trying to analyze this situation and ask how many triangles are possible, well, you don't really need to overthink it here. It's clear that we have a side angle side situation because angle C, if I were to draw that one here, angle C being 38 degrees, well, it's smack in the middle of two other sides. We would, I guess, call them A and B in whichever order, because of course side C would have to be across from it. So we have two sides and an included angle. That's side angle side. And if you think back to geometry, side angle side was a method that we used to prove congruence, which means that if we had one triangle with these three particular measurements and another triangle with those three particular measurements, we had enough information to prove that the two triangles were actually congruent, that they were one and the same, which means that there is one and only one set of possibilities for these missing sides and angles. Well, we can also understand that through what we've learned with law of sines and law of cosines. You have enough information here in this problem to complete the triangle in one and only one way. You would probably start with the law of cosines and work out side C, and then maybe proceed with law of sines to figure out angle A and angle B. And there would be one and only one answer. What we're going to start to recognize is that that is not always the case. This brings us to the real purpose of this video, and that's for the situation that you're going to come across occasionally where you're solving with the law of sines or the law of cosines, and you run into a set of given information that's going to lead to not one triangle, but possibly two. And this is referred to as the ambiguous case. The ambiguous case refers specifically to the SSA situation, where you have a triangle and you know one side, and then you know another side that's right adjacent to it, and then you know the angle that is not in between those two given sides. If that angle was in between the two given sides, we'd call that side angle side. So let's see how the SSA case comes up when we're dealing with the law of sines. Let's suppose you're playing a video game, maybe Luigi's Mansion. So let's just say Luigi's standing here on some sort of a platform, and he's in a room with a ceiling that slopes down like that at maybe some angle. Let's just call the angle 30 degrees to try to form some sort of a triangle here. And right up here at some distance, let's just say a distance of 20 along the edge of the ceiling, you have a wire, and it's 12 feet long. And on the end of that wire is a chandelier. Now I can't draw a chandelier, so I'm just going to draw a light bulb. That's the closest I can do, hanging on the end of that wire. Now the idea is this light bulb or chandelier, whatever it is swinging back and forth, always with a length of 12. And I guess the goal here is to figure out when is it going to be exactly even with the plunger here, or let's just say with the floor level. When is it going to be exactly even so you can fire that plunger and attach it, and I don't know what else. So you can see that there's actually going to be two different spots, one to the left and maybe one to the right, where you're going to be able to complete this triangle. What that means is when we talk about this ambiguous case of side-side angle, like I went through great pains to set up here, you could have a situation where side-side angle can lead to not one, but actually two triangles. And it'll be easy to figure out what those two triangles are as soon as you have a good picture in your head. And this kind of situation here that I've tried to set up, where you have a fixed side, and the fixed side here is represented by the ceiling. That's not going anywhere. And then a fixed angle, and we have a fixed angle here represented by the 30 degrees. And you have to fix an angle by sort of placing the other side, but not necessarily determining how long it might be. You see that the floor, the horizontal there could be possibly different lengths. And then you also have this flexible side. And I like to picture that with the chandelier example here, because it's natural to think of the chandelier sort of swaying back and forth and sort of picturing in your head, where is it going to meet that bottom level? So I always set up my side-side angle problems, my ambiguous case problems, kind of like this. And from here, I can quickly imagine what would happen if I were to allow the light bulb, the chandelier, to swing to the left. So I can quickly picture this triangle right in here. And you'll note that that triangle has what appears to be an obtuse angle opposite the ceiling there of 20 feet. Meanwhile, you also could draw, maybe in the same drawing or in a separate drawing, depending on your artistic skills, a second triangle formed when the chandelier swings out to the right. Of course, it's the same length, and it meets on the same side, and you'll notice that that has an acute angle opposite the 30 degrees and the ceiling of 20. So what we can do is we can use either law of sines or law of cosines to complete this problem. My preference is actually to use the law of cosines to finish the problem, but you can really do it either way. And I'll show you both methods and let you decide for yourself which one you like better. So first we'll do it with the law of sines. So when we're figuring out these two triangles now with the law of sines, the way this would go, I'm going to call this angle here C and C prime. I'll call the acute one C and the obtuse one there C prime. So C prime is referring to the angle in here and C is referring to that angle there. So I'm using the law of sines, and here's how it would go. I would write that the sine of 30 over 12, because 12 is the side opposite the 30-degree angle, is equal to the sine of C over 20. And I'll solve this equation first for the sine of C and then angle C. Now when you do this, the answer that you're going to get for the measure of angle C is always, always, always going to be acute. And in this particular case, you find that the measure of angle C is 56 degrees. Now, if you're wondering why you always get the acute angle, the angle when the chandelier is swinging to the right, and that's because inverse sine always gives you an acute angle. Its range, if you recall, is from negative 90 to 90. So inverse sine, when you're solving one of these problems, can never spit out an obtuse angle. However, in finding that acute angle for the measure of angle C, you also have enough information to work out the measure of angle C prime, the obtuse angle. And that's because you might notice, if you look a little closer here, that what I've formed between the two possibilities for the chandelier is an isosceles triangle. Those two legs are both 12, and that means the two base angles, let's put them in red this time, are both 56 degrees. And of course, this 56 degree on the left is supplementary with this angle C prime. So what that means is once I've got C, I can get C prime just by subtracting from 180. So the measure of angle C prime would be 124 degrees. So now what I can do is I can take these two triangles, which were originally SSA, and I could use this additional information, either C or C prime, to now think of these triangles as side angle side or angle side angle, because I know all the angles in the triangle. Once I have two, the 30 degree and the 56 degree, or the 30 degree and the 124, I have enough information to find the third angle, and then I have enough information to find the third side. However, my preference is not to solve these problems with the law of sines at all. I often prefer to solve them with the law of cosines. So I'm going to back up a few steps and show you how that would be done. Now, the reason that I prefer to use the law of cosines for the ambiguous case is pretty simple. I tend to be more algebraic than I am geometric, so thinking about all the different possibilities of the triangles that can be formed with acute or obtuse angles is sometimes a little too much of a challenge, so I prefer to kind of get right to it with more of an algebraic method. So the law of cosines works by really, instead of focusing on the different triangles that you could form, it just focuses on the missing side. Let's say that we call this missing side here x. Then I'm going to set up a law of cosines expression based around that angle of 30 degrees. So I could say 12 squared is equal to x squared plus 20 squared minus 2 times 20 times x times the cosine of 30 degrees. Just like that. And you'll notice what you have here as you start to work out algebraically is you have a simple quadratic equation. 144 equals x squared plus 400, and then this will be minus 40 times x times the cosine of 30. Now you'll recall in this particular case cosine of 30 is root 3 over 2, but if it were, say, cosine of 31 degrees, you could just use your calculator to work that out. Now rearranging here so that I get a quadratic, I'm going to get x squared minus 20 root 3x, and then it'll be plus 256, which I would get from bringing the 144 over to the left-hand side of the equation. Now this is the job for the quadratic formula, and this is what I mean when I say I've turned the problem more algebraic than geometric. You know that when you solve a quadratic equation, you might get 0, 1, or 2 solutions. And that's exactly what could happen when you're dealing with an SSA case. There was a possibility that I didn't mention when we went through with the law of sines that there weren't two triangles at all. Just imagine for a second that the height of this chandelier was exactly 10. So just going to draw a 10 right here. 10 would be the perfect size to create exactly one triangle, because 10 is the height of the triangle that I've drawn here with an angle of 30 degrees and hypotenuse, I guess, of 20, because the sine of 30 times 20 is equal to 10. And if the chandelier were anything less than 10, imagine it was only 5, then it could be swinging back and forth, and it would never meet that level of the plunger at all. So none of that is a concern when you're using the law of cosines, because the quadratic equation that you get and you solve will lead you to precisely the right number of solutions for your triangle. So let's solve that quadratic. we set up the quadratic formula. You simplify the determinant, and you find two possible solutions here because the determinant's positive. One was x equals 24, and the other was about x equals 10.7. Now, what could happen if you tried a different SSA problem, maybe one that didn't lead to two triangles, you'd see a different kind of number underneath the square root there. If you recall, the discriminant is going to be positive when the quadratic has two solutions, and that's when the SSA will have two solutions. If instead the discriminant were 0, what you'd actually have is a right triangle, and that's what I was mentioning with the chandelier being exactly 10 feet long. Or if the discriminant were negative, then that would be the case where actually there would be no triangles possible, perhaps because maybe you have an obtuse angle and the side across from the obtuse angle isn't the largest side in the triangle. But from where we got to with these two possible solutions for the missing side over here, we can then go ahead and complete the triangle either using the law of sines, or you can use the law of cosines because you know all three sides in the triangle at this point. And when I say complete the triangle, I mean complete both of the triangles. So figure out the triangle with sides 20, 12, and 24, and figure out the triangle with sides 20, 12, and 10.7. Okay, that's a nice little introduction to the ambiguous case of the law of sines.